I have done during my PhD time, and this is sort of a very generalized presentation which I made for something else. But since I thought like there are different background people are here, I would generalize this. So today I'm going to talk about basically the idea is silicon or siloxane-based materials recycling method. And which was it is interesting for me to listen to the previous talk, because they also I mean it was also done Celsius coexanes, which is silicon oxygen bond based materials. So what I'm going to talk about here is basically silicon chemistry. As you all know, this is periodic table, and I'm going to talk about this material and its chemistry a little bit. So polysiloxanes are widely used due to their chemical stability, mechanical stability, thermal stability, and non-toxicity. As a result, these materials are widely used in many industries. For instance, if you think about medical industry, all sort of tubings, nasal tubing, and all the stuff. And if you think about electronics, all your computer-based chips and all the stuff are made from silicon-based materials. And we compare about textile and leather industry. The synthetic leather is made from silicon-based materials, and clothing. And the biggest industry, one of biggest industry is automobile industry. The tubing, hoses, and other car parts are made from silicon-based materials. And the paint industry is basically made from silicon-based materials. And all sort of ladies and gentlemen makeup and other toothpaste and hair cream and all those kind of things are made from silicon-based materials. So in order to this, these materials are readily degrade in soil. So these are the plus points of these materials. So why do we need to recycle this material? That's a big question, because all things are good and it's degrade in soil. So why do we need to recycle this? So synthesis of siloxane or silicon-based material involves a high capital intensive reaction, carbothermal reduction reaction. As you all can see in this video, quartz and coal heated in up to 2000 Celsius temperature, over 2000 Celsius temperature. And as a result, carbon monoxide and carbon dioxide, vast amount of gases released to the environment, which is not good. And also it's not economically beneficial for heating up to over 2000 Celsius. Anyway, once we do this, we can get silicon metal, we called it. And then we can react this silicon metal with chlorine, and then Grignard reagents, and then different reactions we can make silicon-based materials. So I can't see the topic. Hold on. Yeah. So what is depolymerization? Depolymerization is when you have the polymer, we can break that into smaller parts, or in other words, it's monomers. And what are the depolymerization methods that we can use for depolymerization of these materials? One of major depolymerization method is thermal method, and acid-based. By using acids, we can depolymerize silicon-based materials, and bases, alcohols, and steam. So over the years, there are many groups that have tried different methods to depolymerize these materials. I'm going to give briefly the gaps from their studies. For instance, If they use thermal method, basically you heated up that polymer into over 350 Celsius, and as a result, you will get uh, silicon-based monomers, or the fragments starting from N3 to N28. Like it's a very broad formation of monomeric units. And another gap we found was when you use acid and bases, basically you have to add a lot of chemicals, or a higher amount of, it's not catalytic amount, it's equivalent amount of chemicals to depolymerize these silicon-based materials. And if you use alcohols, we have to definitely use another catalyst to and also alcohols also we have to use in equivalent molar ratios. And steams also, we have to heat it materials up to higher temperatures, and we will get a series of monomeric units. And most of all, the biggest gap that, or biggest disadvantage that we found was these all these methods that they have developed, the products that they have make is not thermodynamically stable. So it's difficult to process it further. So because it's converted to, or it will polymerize again. So that was the biggest disadvantage or the gap we found. To overcome that, we design our study. What if we can depolymerize these materials in room temperature and catalytic amount of material by using to depolymerize this material, and we should be able to get fewer amount of depolymerized range products, because then it's easy to convert into something useful. And yeah, so that it will be easy to process further. And for this, we used fluoride ions, since it's very small ion and it can penetrate into silicon and oxygen bond and break it easily. For our initial study, we selected two different or two classical silicon-based materials, which is phenylmethyl polysiloxanes and polydimethyl siloxanes. So initially we selected phenyl group silicon or siloxane polysiloxane, because since phenyl group has ability to attract fluoride ions, so that we believe that it will give our expected results. So we used TBAF, or tetrabutyl ammonium fluoride, as our catalyst, and then THF is our solvent or our medium, and then we just stir that for 24 hours. And once we do that, we quenched our reaction by using calcium chloride. So basically, these are the materials that we used. Those are viscous, very viscous liquids, and also we did commercially available materials as well. I'll explain that. So first, as per the initial study, we did the solvent study, and we found that THF is the best solvent for the depolymerizing siloxane-based materials. And then we did the I don't know, I can't see the topics because of this thing. Anyways, then we found the catalytic. Hold on. Yeah, so then we found we tried to find the solvent volume. I mean, we found that any volume is fine, but when it comes to the solid dissolving, we found that 10 milliliters is much better for that purpose. So that's why we select that. And then we did we found that there's no significant difference in when we increase the catalyst amount. So therefore we selected the lowest amount as the catalyst because of the cost factor. And then these are the characterization or the results that we found. Here, this is the silicon NMR of PDMS. You all can see that D4, D5, and D6, the monomeric cyclic forms, which we found when we use our reaction conditions. And here, this is the GPC of PDMS. And we can see that here it's difficult to see, but what we did was in here with time. So this region is represent the polymeric region. So with time, polymeric regions go down, and the monomeric region represent this one, these two peaks. And so it goes up with time, which means our reaction is working. And then we did the GCMS study, and this is D6 represent this peak, and here you can see D5 represent this peak. And then the smaller the monomeric units, you'll get more fragmentation patterns due to the stability. And here you can see that D4. So now we know that we can depolymerize any laboratory-based pure silicon-based materials. Can we apply that condition to the commercial applications? So we selected several different commercially available silicon-based materials. And this is very important because we never know that this will work or not, since it has a lot of additives in the system and cross-linking and all the stuff. So for the presenting purpose, I have selected Wacker elastocell material. It's a solid one. And here this is the process in action. So this is a solid material. I cut that into the letters in BG since I'm from Bowling Green State University. And when this is in room temperature, without doing anything, no stirring even, you can clearly see this material is completely dissolving or completely depolymerizing. Yeah. So then, so this is the material that we received from. It's a keychain actually. So I cut it, and these are the characterization or the results or the evidence from these materials results. And this is silicon NMR of this Wacker elastocell material. And here you can see the D4 peak, and this is D5 and D6, and you can see that it's a little bit merged together. I believe that's due to the lower concentration. Yeah, but still you can see that clearly it's happening. And this is the GCMS results, and here clearly you can see D6 peak represent this one, and here D5 peak represent this peak, and finally D4 cyclic form represent this peak. So now we know that surprisingly we can depolymerize any silicon-based material. And then so the big question is, can we repolymerize back to its original state, or can we repolymerize back to higher, like upgrade it? And this is the so as I told you earlier, the video shows that we depolymerize that material, and once we depolymerize that, we let it stay there for till the solvent evaporation, and we did not add our quenching agent calcium chloride. So, and we found that when we don't add the calcium chloride or the quencher, it is going back to the repolymerizing without doing anything. So basically, this will repolymerize back if we don't add quenching agent. And then we have done several studies, like these are the regular polymerizing agents: trifolic acid and butyllithium tetramethyl aluminum hydroxide. And we found that we can this is not like uh, this study is just to show that we can repolymerize back, and we did not quantify that or do it properly. This is just to show that we can repolymerize it, and we found that we can repolymerize it back. So the significance of our study is we can depolymerize any siloxane-based polymer regardless of the polymer size or the molecular weight, cross-link intensity, and other additives. And we are using catalytic amount of materials, and reaction is happening under room temperature, which is good for the industry. And basically, depolymerization gives primarily 3 products, and depolymerized products can further process because we are quenching these materials. And the each of these also can be recycled if we want to work towards the greener pathway. And we applied for patent as well, and it was accepted. And I'd like to thank my Bowling Green State University group, and I want to thank green chemistry people for inviting me to share my research with them. So I'd like to know if you have any questions.